Is the combustion a technology of the past? This question is legitimate, considering that up to now, combustion has been strongly related to greenhouse gases emission, especially from the combustion of fossil fuels. Therefore, the true question is, do we still need combustion in a sustainable future? Indeed, most of the energy generated on Earth come from processes involving combustion, especially of fossil fuels, and this had over the years consequences. These stripes show in a more artistic way the global temperature change on Earth from 1850 to 2022. In a more quantitative way, these figures show that the temperature has increased by 1.2 Celsius degrees compared to the period before industrialization. This global temperature increase is undoubtedly a consequence of human activities through greenhouse gases emissions coming from the combustion of fossil fuels. It has been shown that this temperature increase is strongly correlated to CO2 emissions, where every ton of CO2 rejected in the atmosphere adds to global warming. And this must be stopped if we want to keep the temperature increase below 2 Celsius degrees. Hello, my name is Alessio PAPPA. I'm a postdoctoral researcher at the University of Mons, and I'm going to talk about my research topic during my PhD thesis and to talk about combustion flexibility. So far, combustion has been and still is essential to transport us, fuel our industry, make our electricity or warm our houses. Nevertheless, more sustainable approaches must be considered, even though renewable energies come with several limitations. We can point out the intermittent behavior of renewable energy sources, like solar and wind, or also that some industry-related sectors are challenging to electrify towards decarbonization. Hence, even in a fully sustainable net-zero carbon economy, combustion will have a major role to play. But to reach clean and sustained energy generation, combustion must become more flexible, especially in terms of fuel and operation. But we are going to see together what means this word and why we are talking about flexibility. As you can see, I'm standing near a microgas turbine that is able to produce up to 100 kilowatts of electricity. Actually, this is the microgas turbine that I use for most of my numerical investigation. There are several components in microgas turbine, such as the compressor to compress the air, heat exchanger for the heat production, the turbine for the electrical production, but for the thesis we are mainly focusing on the combustion chamber that is just here. These small-scale units can produce both heat and electricity, but obviously it also emits CO2 when running on natural gas. Nevertheless, microgas turbines show a high adaptability to implement advanced cycle modifications, such as cycle humidifications, which allows decoupling heat and electricity production and also increases the electrical efficiency. But we can also consider exhaust gas recirculation to increase the CO2 contents in the exhaust gases to reduce the penalty cost when performing carbon capture. And finally, another option to reduce or avoid carbon emissions is to burn alternative fuels, such as hydrogen. But let's get into it. So, we identified two different needs. The need for operational flexibility with the implementation of advanced cycle modifications, such as humidification or EGR, modifying the oxidizer composition, and then the need for fuel flexibility with the necessity to burn various electrofuels, such as hydrogen. Therefore, these unconventional diluted conditions or unconventional fuels can alter the performance and the stability of the combustion. Therefore, the objective with this thesis is to provide accurate data for real industrial-like burners on the combustion stability, performances, and emissions. To answer this need for flexibility, the research scope of my thesis was using high-fidelity simulation to assess and analyze the impact of unconventional diluted conditions such as water and EGR and/or various fuel or fuel blends on the combustion stability, performance and emissions, especially for microgas turbine combustor. To achieve this research goal, the contribution of this thesis was thus built on three main axes: the numerical tool development, the operational flexibility, and the fuel flexibility. Let's start with the numerical tool development. In the field of numerical simulations, predicting reacting flow behaviors in actual burner leads to a wide range of numerical difficulties when using computational fluid dynamics. First, gas turbine burners involve complex geometries with a high level of turbulence. There are also all the transfer mechanisms such as heat and mass transfer, and finally the turbulence chemistry interaction. To deal with these difficulties, different models can be used for turbulence modeling and chemistry modeling. For turbulence modeling, I worked with large eddy simulations. This approach offers a balanced solution between fidelity and complexity. In addition, this approach combined with a finite rate chemistry approach, also called complex chemistry, allows assessing combustion instabilities, especially under the unconventional conditions and fuels we want to consider for this thesis. Regarding the meshes used for my simulations, I had the opportunity to work on the development of adaptive mesh refinement to combustion applications. This video shows that the adaptive mesh refinement algorithm dynamically refines the mesh all along the flow simulation, where the mesh refinements follow the flame shape evolution and any flame fluctuations. This implementation of algorithm allows optimizing the cell distributions on the domain. It also reduces the human effort during the meshing phase of a CFD project. Finally, any flame stability analysis requires high-fidelity computations, such as large eddy simulations, but the computational cost can quickly increase with the configuration and the required accuracy for turbulence and chemistry. For example, LES running on a supercomputer requires, on average, 25 days on high-performance computing using 1000 CPUs. This corresponds to 6 months on a working station and 9 years on a simple laptop. Therefore, during my thesis, I also developed an hybrid 0D 1D model coupling chemical reactor networks with 1D flame calculations, allowing low-cost predictions of any combustor performances and emissions using a simple Python code. The numerical results obtained during the PhD thesis were made to answer several questions. First, for the operational flexibility, we can wonder what is the impact of diluted conditions, such as humidification and EGR, on the flame. And then we can wonder what are the stability limits when performing diluted conditions, so how far we can push the dilution. And for the fuel flexibility, we can wonder if it's possible to safely burn hydrogen without any combustor redesign. For the first question, we performed large eddy simulation to assess the impact of moderate dilution level of water injection, EGR, and combination of both. Regarding the stability limit, by using the simplified 0D 1D model, we were able to define the range of stability between blow-off and flashback to know in which operating conditions we can keep stable combustion. For the last part, all the observations, conclusions, and developed numerical tools helped to work on hydrogen combustion. Indeed, hydrogen combustion is well known to lead to flame instabilities with risk of flashback apparition. Here we have an illustration of results of a mixture fraction of 50% of hydrogen and 50% methane, where we can see that premix burners are not adapted to burn hydrogen blends, where we can see a flame front going back through the injectors. And this can lead to critical damages to the facilities. Literature provides several solutions to avoid such flashback issues, but most of them require to modify the combustor geometry. But for more flexibility, we can understand that stabilization must be achieved without any redesign of the combustor. So the idea provided by this thesis is to use diluted conditions from existing advanced cycles, such as humidification and EGR, to slow down the reaction rate, temperature, and flame speed. So the main goal of this part was to work on flashback prevention for various hydrogen blends without any redesign of a microgas turbine combustor. And this work is split in two parts. First, using the 0D 1D model for fast prediction of the operating conditions to avoid flashback, and then 3D LES for the stability analysis. Let's see now if the predetermined dilution levels allow avoiding flashback. I already showed that flashback occurs for a mixture fraction with 50% hydrogen. And here are the LES results of the time average and fluctuations of the reaction rate, where only the region near the injectors is shown. First, with the same mixture fraction, by applying humidification in EGR, we can see that flashback is avoided. Then, the results show that we are able to burn up to 100% hydrogen without any flashback when performing new humidification, but not with EGR. Therefore, the LES results show that the proposed methodology allows avoiding flashback without any combustor redesign. Let's summarize this work in few highlights. The strength of this thesis lies in the development of models using large eddy simulations combined with complex chemistry to simulate turbulent combustion in actual microgas turbine combustors geometries. Regarding the originality and novelty provided by this thesis, first on the numerical method part, I had the opportunity to develop an hybrid 0D 1D model for fast prediction, and to develop adaptive mesh refinement adapted to combustion applications. On a more application part, I had the opportunity to work on flashback prevention without any redesign of a microgas turbine combustor. So, do we still need combustion in a sustainable future? I believe we do. By becoming more flexible, combustion has a major role to play. First in the energy transition, and then in reaching a fully sustainable net zero carbon economy. This thesis brings some insight and different passes using both fast prediction numerical tools and high-fidelity simulation to push further the flexibility of combustion processes, especially by bringing important contribution in the field of microgas turbines.